We have seen how a changing magnetic field generates an electrical voltage, and how conversely an electrical current produces a magnetic field, and hence can produce a force on another magnet. Let's see now how these phenomena can be turned into practical generators and motors. This can be done by winding a coil on a rotor. Let's say first that we have a coil. I'll just show it as a single turn for convenience, but in reality, of course, there would be many turns. We place this coil on a bearing so that it can rotate around its center. The bearing in the diagram is shown by the black dotted line. If the coil is forced to rotate by, for example, a water wheel or a wind turbine or an internal combustion engine of some sort, the field changes because sometimes no magnetic field lines pass through the coil, that is when it's parallel to the field generated by the magnets, and sometimes lots pass through it when it's at right angles to the magnets. We can tap off the resulting electricity generated using a slip ring system as shown in the diagram. The voltage or current generated like this can be plotted on a graph with the voltage or current on the y-axis and the time on the x-axis. If the rotor starts at a position when no voltage is generated, it will rise as shown in the graph when the rotor turns, and when it reaches 180 degrees, the voltage will go negative. This type of plot is called a time domain representation and is shown practically on an instrument called an oscilloscope. This is a very common way of showing a signal, that is voltage or current plotted against time. The generated signal in this case is called a sine wave because it can be described by the mathematical formula or equation for sine. An electrical motor just works in the opposite way. This time we apply the voltage to the coil, and as we learned previously, this makes it into a magnet. Because of the interaction of its magnetic field and the magnetic field of the magnet, it starts turning. When it's halfway round, we need some, typically mechanical contrivance, to flip the plus and the minus terminals around. This will ensure that the force is always in the same direction. Finally, let's note that several sensors actually work using these principles. One of the most common is a dynamic microphone, which is the type of microphone often held by hand on stage by singers. In this case, a thin diaphragm vibrates because it is exposed to the air. Attached to this diaphragm is a coil of wire which moves up or down in sympathy with the diaphragm. In the middle of the coil is a magnet. The principle is, as we saw before, the magnetic field in the coil changes because the coil is moving in relationship to the magnet. This causes a voltage. But the voltage this time reflects the air pressure fluctuations which cause the diaphragm to move and therefore represent your voice.